Good afternoon, everybody. My name's Jim, and I'm Neo's chief scientist. For historical reasons, we have far more capable scientists on board nowadays. Thank you for... Okay, I've meant to talk about stuff, but thanks first. It's been a really splendid day. Thank you for everyone for coming. It's been great. I've loved talking with you. I've learned so much from speaking with you and understanding what you're graphing, and the other speakers. I've learned so much from you, including TV's David Simons. A little bit of celebrity there. I'm hoping to rub off. Obviously not literally. It's good to be back in the UK. You say that in the US and like you get banged up for, blasphemy or something. Anyway, so thank you so much for coming today. It's been an absolutely spectacular day. I've thoroughly enjoyed it. Thank you to you orange-shirted people for chaperoning us and shepherding us around. It's been super for you. Thank you for you guys for taking a day off and coming to this big, messy graph fest. I hope it's been extremely useful to you. So I get to close out, which is nice. Sort of Emil's job in the morning is to kind of welcome you and get you like engaged and all that. I think my job is to just clear the decks so the cleaners can get in, and at least that's the way I've come to understand it. So my talk's really about being ambitious. And I think, talking to some of you guys today, there's a lot of ambition in the graph community. We're doing some really ambitious things. And I just want to kind of take a look at where we've been in terms of building graph-based systems, where we're going next and where we're going in the future. Because as a graph guy, and you folks as graph practitioners, not only are we currently building some rather ambitious systems, but our ambition seems to be growing. And as the tech grows, our ambition grows, and as our ambition grows, the tech grows. So I'd like to kind of take us through a past, present, and future of where we're going in graphs with an eye on Neo4j. But first, there are some indignities to be undone. I'll make my own indignities later. When your boss is in the front row looking at you, it does feel somewhat constraining, actually. You actually do have a piercing gaze, yes. But how does your piercing gaze work versus a laser pointer? You brought a piercing gaze to a gunfight. Anyway, so we do have to, it turns out that, this morning, my boss with the piercing eyes, the piercing gaze, I thought, it was right to say that we've released a new version of the Graph Databases book, right? Which is a nice book, and he had a hand in writing it. When he finally gets around to completing his submission, he did a great job. And we also said that we are going to be dishing out copies of that book for you guys who did the funniest, best, most pertinent, most flattering to Emil kind of tweets. We are going to do that. We're going to tweet the winners, because otherwise I've got to do it during this keynote, and it's just going to turn into a big bookathon. But I did feel, when Emil was going around like, my book is so awesome, which is kind of how he sounds, right? I did feel somehow awkward, right? Because lots of people now are writing Neo4j blog posts, or writing Neo4j demos. Some people are even writing Neo4j books, right? I mean, there are other people in this room who Emil chose for some inexplicably mean reason not to mention, who have written Neo4j books, right? Who have done a great job outside of the mainstream of O'Reilly, outside of, let's say, the prestigious tier of publishing, who have, written very well-received kind of B and C tier level books. I mean, for example, I do feel that taking the piss out of a 2.5 meter tall man is not good for my health, but here's where we are now. I do feel that Belgium's finest English language book on Neo4j deserves a special call out. Obviously, I caught Rick yesterday before he'd had a shave. He's kind of anglicized himself for today's event. But Rick, where's Rick? I can't see his lights. I just hope he's not behind. He's behind you. I do think that Rick's book deserved a special mention there. I mean, I do feel a little bit sorry for Rick, because his book is only in the first edition. And how many languages, Rick? Just one. Was that 2, or was that fuck you? Okay. But, you know, not all of us can have a successful O'Reilly book in English and Japanese. But, Rick, if there's anyone else that can do it, maybe you in a year or two. Anyway, so actually what I do want to talk about, so I've broken this talk down into like 3 distinctly nerdy phases. So Star Wars theme. So we're going to talk about how graph databases have revolutionized data in the relatively short time that graph database has been around. I think they've had a profound impact in the way that we deal with data in systems. I then want to look slightly forward and say, well, given that graph databases have helped us to revolutionize systems, what might we do in the near future to match our ever-rising ambition? And then what might we do in the very long term? And I've split these helpfully into episodes 4, 5, and 6. So, back in the day, they are so old now. Have you seen the trailer? They're like, it's like Granddad Solo. Anyway, back in the day. So back in like, the Star Wars era, the world was a bit different from what we know now. The world was actually a lot more homogeneous. You know what? You guys down here get short shrift. So the world was a lot more homogeneous, right? It was square, like we all had the same stuff going on. The data about us was, oh, now I feel bad about those guys. Oh, well. The data about us was quite square. We had, like, for example, the same payroll data. It's kind of tabular or square. We had the same, like, social welfare provision data. I mean, at least we had social welfare provision back then, but we may or may not have tomorrow. Let's see, eh? But the point being that the world was square, and the predominant metaphor that we used to capture data was tables. In fact, ultimately, the kind of databases that we saw emerging from E.F. Codd's phenomenal work building on predicate logic were the tabular databases. I really am upset that they got relational first. Because, like, we do more than that. But anyway, so back in the 70s, this is what happened. This is the genesis of the modern database as we know it. I love this. I do love this guy here. He looks like my Uncle Jim, actually. But notice, like, this is obviously a strike, get used to them. This guy is so on strike, he won't even move his hands from his pockets. That is a radical right there, right? He's my favorite guy ever. Look at that surly expression. He's like, yeah. It's like when Emil says, like, do work. I'm like, so back in the 70s, this is what we had. So the genesis of the modern data movement, actually. So no cheeky RDBMS stokes. I really think this is really where we all came from. Then in the 80s, this stuff started. Oh, gee, Jim, I wonder which side of the political spectrum you're on. I don't know. So in the 80s, that kind of research stuff really became mainstream. So, we had the emergence of the world's dominant relational database organizations, things like Oracle and IBM, so on, really started to push relational technology. And it's kind of okay, because at that point, we still had sort of tabular data and so on. And so it kind of worked. But then if you go a little bit further in time, you find that as our ambition grew, so did the complexity of the models that we were trying to build in the relational database. So we ended up kind of, by the way, thank you for sending that schema over to me. It was pretty useful. There's several of you in the audience thinking, fuck, how did he get that? Tables, meh. The problem is you've got schemas like this, and some of you in the audience are still super capable at relational databases, and you can kind of see the intent of this schema, right? It's actually the Drupal schema, don't worry, it isn't yours, but it just looks like it. You can kind of see through the schema to the underlying intent. And I got to say, without a word of jest, that's super impressive. But it's accidental complexity. These kind of complex schemas are difficult to read. They're difficult to transfer knowledge with. And they also eventually imply pain. Why? Because no matter how good your relational database design, at some point you join. And the first join you do, you're like, I got away with it. And then the second join you do, you're like, got away with it again. And then all bets are off, right? And eventually you all do that and the systems become awful and shitty. Why? Because we've started to push hard at the boundaries of that envelope. Tables become problematic. It's hard to fit in the kind of, very semi-structured, regular, irregular, all kinds of modern data. It's hard to push into them. And you guys know this because in your code that interacts with the database, you've got a shit ton of if-null checks. Yeah? I know that without seeing your code because it's just what happens. So why? Well, accidental complexity, not to mention the fact it's built on sets. So as a young man, oh, wow, left me hanging. No, Jim, you look so young. No. Tough audience, man. So as a young man, I was taught relational calculus by some really, really lovely people up at the University of Newcastle. And it's got a short A, in case you Southerners were wondering. This bugged me. So I'd learned, relational calculus. I could kind of get the kind of, the Greek-looking syntax. For my colleague Christos over there, it looked like a spelling test. But it made sense to me, right? It was just kind of a way of describing systems. And then I was given access to a Unix time-sharing machine, which we nowadays know as a Linux laptop. And it ran a database called Ingress. Ooh, yeah, you can age me. You can age me like a tree cut through the middle. And then I discovered that actually to make the database do the kind of tricks that I'd learned in the purely mathematical realm, there was shit like this going on. And I'm like, excuse me, Professor Elbow Patches, is a hyphenated name. Oh. Like WTF, before it was a thing. And why isn't it just that customers have accounts? Why do I have to do this, like, artificial, accidental complexity stuff? And the answer I got back was actually fundamentally compelling. And he said, shut the fuck up and do the exercises. That's why. So that's a bit kind of a disappointing answer. So we can see this. There is a graph struggling to get out of this data. Later on, a few years later on, I was drunk off my arse in southern Sweden, and I was working with Ian Robinson, top-notch Ian Robinson, as he's now known. And there was this guy that I met, and I'm kind of describing some telecoms domain to him. He's like, oh, there's graphs in your data. I'm like, don't be an idiot, man. Do you know how databases work? There are tables in my data. Awkward, because he's now giving me his piercing look. But ultimately, there is a graph struggling to get out of this. This kind of accidental complexity, when you multiply it out by the kinds of complex, sophisticated models that we're building, it ends up being problematic, right? It ends up being a massive bomb, join pain, waiting to go off. Oh, there we go. One more. This is way better than anything I've got to say, to be honest, so. All right, so eventually you get this complexity snowballs out of control and you get the nuclear budgie. Fast forward now into the 1990s. There are already some people in this decade who aren't caught up in app servers and ORMs, although admittedly that rules out 90% of the computer scientists at this point. But there are a bunch of people who are starting to think about large-scale, mostly physics or porn data at global scale interlinked, right? And this is the guy, right? This is Tim Berners-Lee. Where are the Belgians? I know a couple of you. Who's the other guy that invented the web? Who? Anyone else ever heard of Robert Caillot? Sucks to be Belgian. So this is Tim Berners-Lee, who solo invented the web with no help from any Belgians whatsoever. And Tim's thinking about what it means to have like massively scaled data across the world, like the World Wide Web, and what it means for that data to be interlinked. He's effectively thinking about what it means to have the first really, really big graph of data. Of course, we use it for like, movies and porn, but he has more sophisticated things. Then, enter the 21st century, and we got new vocabulary. So not only do we have the World Wide Web, which sounds rather big on web scale, but we start to get other interesting data technologies from the leading web companies, right? I'm giving the camera dude a really hard time here. Oh, no, he's good. He's drawn a bead on me. So we learn new words, right? We learn words like web scale and Google scale and so on. And this is great, right? Because we're starting to deal with larger volumes of data. And what these guys are doing I think is remarkable. Not the kind of X-scaleness of it all, but these are big web properties, the Googles and Amazons and so on. But they're starting to do something fundamentally different. They're not just buying off-the-shelf relational technology anymore, which is like, why? Because that stuff's great. You buy it and put an ORM on it and declare victory or difficulty, depending on your point of view. Well, these guys have sort of started to observe that the model of the traditional relational database isn't terribly helpful for the kind of systems they're building. And in fact, the conjunction of sets, the Cartesian product of sets problem that comes when you join through those models is actually an inhibitor to getting their business done. So these guys are actually starting to build new kinds of databases, which is all kinds of weird, right? I mean, I guess many of us in our lives have built web-based systems for deployment to consumers. And often, you know, you're doing your kind of typical agile thing. You take the card from the wall. It says, like, change the CSS. And you moan because you hate that card, but, you know, you go away and do it. Imagine going up to the wall. It's like, take the card, invent entirely new kind of database. I'll have that one. Who wants to pair with me? Like, poof. Right? So these guys are doing something really fundamentally interesting. And what they've done now is set the scene to say, actually, there isn't a one-size-fits-all database. There are data storage, query, and processing needs that are potentially unique to your situation. You should be able to pick the tech to deal with them. So NoSQL comes charging to the rescue. I included this at the American version of GraphConnect just to worry them. It did. They were, you can see the visceral reaction there. So NoSQL comes charging to the rescue. And this is great, right? So based on what the big web properties were doing, a plethora of alternative databases became available to regular folks like us building regular systems. The majority of the NoSQL databases were what Fowler and Sadler's call aggregate stores. So there's a chap called Martin Fowler who's quite a big noise in software and systems. And he wrote a really nice book called NoSQL Distilled with Pramod Sadler's. And in that book, the Fowler and Sadler's observed that most NoSQL systems are aggregate stores. That is, you know, they store values by key, or they store documents by key, or they store columns by key. And Fowler and Sadler's say that these systems work really well where the storage and retrieval patterns are symmetric. So you store a customer, retrieve a customer, store account, retrieve account, that kind of stuff. And those systems work very well when you've got a symmetric pattern like that. Where you have a different pattern, where you want to slice and dice the data, these kind of systems end up asking you to compute an answer. So you export some records out of the database, you run them through some processing infrastructure, and you compute your way to an answer. That's why aggregate stores talk so much about MapReduce. But how does that work then when you've got fundamentally connected data? Now here you can see a trivial social network, right, in an aggregate database. Now you can see that because you're humans, probably, and Swedes. But you can see that because your clever human brains are inferencing stuff. You say, okay, so I've got some users with their ages. And I can kind of see implied here that this Jeff person is friends with this Sally person and this Gaza person, and Gaza is friends with Jeff, bromance. And you can kind of see implied linkage there. So if you were to extract these records and compute them through your MapReduce infrastructure, like your Hadoop infrastructure, kind of drag them out of the database where they love to be, and like drop them in the Hadoop sausage machine, and then turn the handle. This is real time, by the way. You could have done it on a laptop ages ago, but it's not that curve now. It's gone down a bit. If I do it one more time, there, back up the funny curve. Anyway, so you could process that, and you could probably try and imply some of these like friendships, some of this social networking. What the database doesn't understand is the constraints here. You know, if I delete this Gaza record, there's no reason why the database should help me also delete this property here, right? So I end up with like dangling relationships and stuff, which is a bit kind of crap. So what you end up doing if you've got an aggregate database is kind of reifying out of this the kind of view of the graph. Now, reify, it turns out, is a euphemism. Reify means build your own version of Neo4j and fail doing it because it's bloody hard to do. Instead, you could just use something like a graph database, Neo4j, right, where your relationships are first-class entities in the data along with the records themselves. But I've got a bad feeling about this. People still want to use aggregate stores because it's what they know. But what if we wanted to sell things to our social network? So sure, you could probably have the gumption to figure out, you know, a kind of FlockDB style shallow graph over your document store or your aggregate store and try and keep it somewhat in check. But now what if you wanted to do something more interesting, make social recommendations, right? Well, let's see now. In an aggregate database, I could choose to store it like this, where I've got these implied links where Gaza bought some headphones and Sally bought some record players. Where was I born? In the 1920s. You know what I mean? Decks, some headphones, and you've got the product records here. Again, in order to make sense of that connectivity, you need to process, to compute across that data set in order to reify out that data. In a graph database, this is trivial because these relationships appear as first-class citizens in your database. On my laptop, which is lovely, by the way, the last time I gave this talk in front of my piercing-eyed boss, I actually had an old laptop, and I was like, oh, this is kind of a shit laptop. Now I've got a new one. I'm just saying, the squeaky wheel gets the oil. On my lovely brand new spanking laptop, I can traverse one of these relationships at the rate of, in a steady state database, at the rate of about 12 to 14 million a second. So that's super, super cheap for us to do that. Doing the same kind of number crunching across many records in an aggregate database, I don't know, all bets are off. But it can go from bad to worse. What then if we wanted to go and do more sophisticated, even recommendations? What if I wanted to recommend common use case, what my friends buy, or what my friends of friends buy? Once you go past friends of friends, you just start getting weird recommendations. You don't want to go that far, right? That's bottom of the barrel stuff, right? 3 levels out. Doing this in a relational, in an aggregate database, it's a tough job because you end up processing, computing across so many records. In Neo4j, find the record that represents you, traverse out to your friends, and traverse out to what they bought. Done deal. This is all kind of sub-millisecond scale, happy, happy days. Let's reflect for a moment, right? This stuff, right, actual sort of content, deadpan. Okay, yeah. Seriously, are you IT professionals? My goodness. So, side note, it is relatively off-putting when he stops paying attention and starts frowning. It's genuinely not helpful. Anyway, look at the minion. No, the cartoon, not me. I know. So this is good, right? Because what it means is for kinds of the systems that we're already building today, there are great solutions, right? You can build comprehensive, performant recommendation systems, a whole bunch of stuff today. The technology is there to meet and exceed your ambition today. But all that means is it's like a red rag to a bull. Oh, we can meet or exceed your ambition. Well, fuck it then. I'm going to be more ambitious. Ha, 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 ha. Which is fine, keeps me in the job. But we're at a really interesting juncture in the road now. Alistair, glad you could make it, mate. Here's your slide that I nicked and credited you. Now, Alistair says that we're at a really interesting crossroads. On the left-hand side of this fork in the road, we have got most of NoSQL, where the model is to denormalize your data into keys and values or documents or columns or whatever. And while that is a simple data model, in order to extract intelligence from it, in order to extract insight and knowledge from it, you have a compute-centric model, the MapReduce-friendly style database. On the right-hand side, you have the graph databases. The graph databases, the graph model, the label property graph model, is absolutely the most expressive data model I've ever come across, where you have a network or graph that you traverse in order to find your informational goals. In that sense, it shares something with the relational databases, insofar as you build a high-fidelity model of your domain, and then you ask questions of that model in order to gain insight. The benefits being that this kind of stuff is absolutely quick enough to go between a web request, web response. Or it can be flipped into an analytical mode where you can send sophisticated graph theoretical queries at it and let it run for minutes or hours or days to come up with massively sensible insight. I think we're going this way. You guys have a bit of a hunch that we're going that way because you're all sitting there, unless you've accidentally mistaken this for Strata, in which case, wrong building. But let's do some use cases. Look, man, the amount of jokes I need to squeeze into this 40 minutes, 1 or 2 of them are going to fall flat. Just accept that on average it will be a giggle, and now and again, just let it go. Let it go. Let it go. So there's a bunch of really interesting stuff, some of which that you've stumbled on today, some of which you've had hallway conversations about. But in terms of what we currently do in graphs that's really interesting and ambitious, players like Telenor, so big telco in the Nordics, and what those guys have is was an enormously cumbersome way of understanding effectively entitlements, so account management and entitlements. Given that I am a mobile phone user, what services do I have access to through the various subscriptions, or indeed through the various business departments which hold my subscriptions and blah, blah, blah. This is not conceptually a very difficult problem. It's a natural graph problem. But the tech they used to have that did this would just grind away at it for hours because under the covers it was a relational database. Now, relational databases are fine things. They are mature. They are based on a branch of mathematics which is mature. One of the things that relational databases don't like, though, is joins. And when you're trying to mimic a path-based operation in a relational database, you do joins. You typically do recursive joins. But you guys have got that table, right? The join everything to everything through everything table. Yeah, there's a few of you laughing, but it's like, yeah, but now I feel kind of uneasy because I do have that table. And the problem is that when you start joining stuff together, things slow down. You convert this to a graph and tell all this classic minutes to milliseconds kind of story for Neo4j. So you take a system that used to take far too many minutes to run, you convert it over to a graph, and admittedly it means learning a new piece of tech and deploying a new piece of tech, but the value on that investment is enormous because those queries go from an untenable minutes to a very, very pleasant milliseconds. Beamly, local boys, formerly Zbox. Third screen provider, that is, any Beamly folks in the house? Love. Glenn didn't make it. Sad times. He gave me some nonsense excuse about having important work things to do, but lovely, lovely Beamly. So third screen experience, because it turns out watching TV is not enough. You need to watch TV with people who aren't physically with you. I'm a dad, right? I got to say, on the whole, when I get minutes to watch Doctor Who, the last thing I want to do is have people with me. But I realize I'm not the demographic. So Beamly, interestingly, right, so there's a bunch of TV metadata. And you and I think TV metadata is really simple, right? It's the magazine from the Mail on Sunday with all the listings in. Oh, giggles there. I think we spotted an inconsistency in my storyline. It's just, channels and programs, right? Doddle. No, turns out that actually TV metadata is phenomenally complex because TV stations broadcast the same show. They have repeats. They have catch-up channels. They have youth-oriented channels that occasionally pull in other. It's like a nested web of TV metadata, complicated by the fact that this stuff then goes international. So what Beamly had was a relational database that did this slowly. And as I understand, your migrations were horrid and painful and flaky. Beamly took 2 years ago now, 2.5 years ago, a while ago, it seems like ancient history in IT time, took the decision to move that metadata into the graph. Again, classic minutes to milliseconds. Migrations aren't a problem anymore. All you've got are TV shows and links to their channels, links to their repeats, links to their +1, and so on. Take the complexity that's foisted upon you and the latency that's foisted upon you by the wrong kind of database, drop it into a graph, and peace and love ensue. Now, there is so there's a guy called Volker who many of you have met because he's he's a bit of a social butterfly, and he works at a company. I can only describe this company as Trotter's Independent Trading Co. on the web. That's for my people. For those of you from outside the UK, Google. And so what Volker and his mates invented was effectively a secondary marketplace in courier capacity. So subsequently, they were bought out by eBay. Now, last time I saw Volker talk about this stuff, he eBayed himself a bottle of whiskey. Stressful job, huh? At the start of a talk he was giving, and the guarantee that the eBay Now service gives is that that bottle of whiskey will be with you by the end of your talk. Is that the quality of service that you set? Yeah. And it did. So actually what eBay Now give you is the ability to get goods transported from buyer to seller in a metropolitan area within a certain time frame. Now, Volker's very smart. He's like Dr. Volker. He's German. He's got a PhD from MIT. Right? That's smart things right there. When Dr. Volker first built this amazing contraption, he built it on MySQL. So, I don't know, a little bit. No? You told me it did.
No, they built it.
Oh, they built it. Oh. Was it? So they built it on... It's right. I mean, all those systems that they built, they were rubbish. So they built a system on MySQL, and given the parameters of your purchase, they could come back to you with a time slot when you get it delivered. Took about a second, give or take. There was something I heard that was pub speak, though, that you got the real world and the computer world mixed up. And they had on that system the latency of their longest query in computer time was longer than their shortest physical delivery. True story?
It's true to some extent.
True to some extent. True story. We only do Booleans here. I don't need your fuzzy logic maths, boy. Pipe down. Now, they still have a system which takes about a second to return a query. Faster now. How many options does it give me now?
I think it's for 2 days and 500.
2 days worth of delivery options in half a second, going from 1, take it or leave it, in a second. Again, that's that fantastic, by applying just a little bit of PhD level mathematics and Neo4j, you too could invent the next great. But again, it's one of those things where the technology just takes all of the accidental cruft out of the way and allows you to perform and get some really valuable jobs done. Because I do want that second-hand iPad now, not tomorrow. Right? It's important to me. Emil talked about this one, a grown-up logistics company, not like some scruffy little startup from the East End, had the same problem. So they had a problem where their parcel delivery is actually way more exciting than Emil presented it. It's the Swedishness. It kind of sounds a bit conservative. Turns out parcel delivery, things happen. It used to be you want to send a parcel back, so you'd have to wait for it to get to your house, decide you didn't want it, send it back. Now you can reject parcels while they're in flow. Like you can say, I don't want that, and it never even reaches your house. This stuff's phenomenal. Volume's going up, but ultimately we know that parcel routing of any kind, is what graph theory was made for. It's where it came from. So there was a Neo4j-based solution in Europe's largest economy, whereby they were able to plot delivery routes nationwide. And as parcels were flowing along those clever conveyor belts with laser scanners, they were able to reroute the parcels for their most optimal destination. Now, I also heard some hearsay about this, that when confronted by an Oracle database person about this solution, the very lovely architect of this solution patiently listened and said, oh, no, that's not possible. And then the Oracle guy insisted. And then, as I understand it, the very patient and polite person that architected this system said, well, while you've been arguing, my system has just routed 10,000 parcels, so please sit down. Which I thought was the loveliest genteel smackdown. Then you've got Froth City, aka Silicon Valley, right? Everyone wants to be in Crunchbase. Obvious use case here. So this is a kind of, anyone watch Silicon Valley? Anyone live there? So they are all kind of incestuous weirdos over there, as we know. And what they want to do is put all of their kind of like entrepreneurship and like venture capital stuff in a graph database. So Crunchbase runs on Neo4j, and actually, all joking aside, provides a bunch of value about companies. You can find us on there, and their links, their investors, who else their investors have invested in, and so on. Walmart, okay, not necessarily synonymous in our minds as being a tech company, but Walmart used Neo4j for recommendations. This is the F1 company. Right? There is no argument about, oh, yes, but we're a big enterprise. We can't possibly use that emerging graph tech. Yeah, you're big, but you're not that big. Boom, done. How? How do we do this? Well, you build your domain model, you deploy it on clusters of Neo4j. So clusters of Neo4j work brilliantly for the kind of systems that even Walmart are building. We have our lovely clustering architecture, which is sympathetic to graph workloads, which is to say it's extremely competent at farming out reads, graph traversals, and then allows you to do lots of ACID transactions per second on it, which is great. And in fact, there were a couple of people in the room who even built Paxos to make all of that happen, right, guys? Yeah, I think that's Leslie Lamport. I'm not sure. It's not. Are you sure? Really? I don't know, man. I Googled it, and that's what it said. So this is pretty straightforward. Neo4j clusters work today in a very vanilla way. It's very unsurprising. You have a bunch of machines that get hooked together in a cluster. Actually, under the covers, it turns out to be a leader-follower kind of style architecture, but you can write and read to any of these machines. This stuff also works at global scale. So you've got people in the room, like certain Swiss investment banks, who are deploying Neo4j in a very geographically dispersed way. Adobe built Creative Cloud in this kind of way, so multi-DC Neo4j. So what does this mean? It means even if you've got very geographic, you can't laugh at it a second time. Despair. Kids of today. So what does that mean? It means that even if you've got very geographically dispersed systems, you can still build them and have high confidence and high ambition building on today's Neo4j. So, Act 2. So, remember episode 5, it's the dark one, right? It's the good one, actually. What have you got? You've got a bunch of rebels who've like inflicted a little bit of an embarrassment on a shoddily architected IT construction project. Apparently, a port was left open. I don't know. So you've got now, so what happened is, the rebels, they've still got basically no resources at their disposal, but they're a little bit more ambitious, right? So it's like, right, now let's up the ante, let's do something really good, like go to a really cold planet. Well, you know, Sweden. So what might we do then? So we might look around, this one only makes sense to the Doctor Who fans. We might look around and say, well, what have we got that we could kind of bolt together in some kind of like Frankenstein way, whereby we could kind of get like the loveliness of Cypher and stick it on some like, you know, some back-end database engine, and then kind of get the best of both worlds, get the kind of beautiful Cypher, and then like the magical scale fairies make all of the other problems go away, right? So obviously then, what the rebels need to cobble together is something that's eventually consistent, over write consistent, base over ACID, and partitioned over single image, right? That's totally obvious. Yeah. Wait a minute. I think there are a couple of guys that you need to meet first. This is Tom and Pete. They're lovely guys. They're a couple of Geordies. So they're only drunk most of the time. They wrote a book, like when books came on paper. It's a good book, actually. It's Fault Tolerance, Principles and Practice. And these guys are actually, you know, kind of experts in fault-tolerant computing. They were both PhD students of Brian Randall, who was the guy that coined the term software engineering and is himself a well-renowned practitioner of fault-tolerant computing. These guys are interesting. They're not necessarily database guys. In fact, Pete has an interest in parallel computing, and Tom has an interest in safety-critical systems. But they wrote this really nice book. And the thing about them, that I know them. There's a graph that we should maybe look at. It turns out that Tom was my undergraduate supervisor. That's nice. And Pete was my PhD supervisor. There's a little graph for you there. It's nice. Kind of, that's what I get paid for, right? I get paid like 100 quid per graph. That's what happens. So there's a more interesting graph there that I think we might want to have a look at. So actually, you know, if we were to model this as Ian Top-Notch Robinson might, then you might say that actually Tom created a supervision agreement for my BSc degree, and I agreed to it. That seems like a reasonable graph. And the next step, lovely linked list here. Linked lists are awesome because they impose ordering on events. That's splendid. And next there was an end of semester interview, which Tom conducted and I participated in. And next, Tom laughed his balls off at me because I told him I wanted to do a PhD. And he just, seriously, he just laughed. He was just like, at me as well, targeted at. It was kind of personal, right? I was like, all right. I was a diligent student as well. I was diligently in the pub every night. Anyway, so Tom laughed at me, but then the graph gets more interesting because then a supervision arrangement was agreed between me and Pete, which Tom negotiated, which was nice of him. And then one final bit of the graph, which I can only infer, doesn't take a fancy pants machine learning algorithm to figure that one out, does it really? Anyway, oh yeah, sorry, I meant to be giving a talk about graphs. Get on with it, Jim. So these guys know about this concept of dependability, which is the measure of a system such that you have confidence in it. And dependability is you know, broken down into these 5 classifications: availability, reliability, integrity, safety, and confidentiality. Now, the truth of it is that I am not at all confident about talking about 3 of these. They are beyond my area of expertise. But I do know a little bit about these 2, having worked in the database space and the distributed systems space for quite a while. And they're quite interesting, right? Because there's a little bit of tension there. So you've got availability, which is that the system is going to provide service. It's on. It's responsive. And then you've got reliability, which is that the system will tell you the correct answer when you ask it. And these are, well, it's a bit annoying, isn't it, that they're separate? Because ideally you'd like for there to be the system is on and behaving correctly, that one unifying property to rule them all. But it turns out that they are not. And in fact, we've known this for a long time. The distributed systems community has known this for a long time, in the olden days. And we know that from FLP that in an asynchronous distributed system, so FLP is Fisher, Lynch, and Patterson. It's a paper from 1985. And in that paper, Fisher, Lynch, and Patterson observed that if you have an asynchronous system, which is to say a computer network, you can pick 2 of these 3, but never 3 of these 3. And this by the way, for those of you who are cap conjecture, cap theorists, this predates cap. You can have safety, that is your results can be valid and identical, all nodes at all times. You can have termination, so your algorithm will finish. Or you can be fault tolerant, that is the system can survive the failure at any point. And you're allowed to pick 2 out of 3 of these, which is annoying, because I want 3 out of 3 of these. Right? But your architect wants 3 out of 3 of these when he inevitably says, I want a system that can give guaranteed once-only delivery of messages. And when you say it can't be done, he's like, well, you're just not working hard enough. But now you know the answer. You can direct him to this paper and tell him to go fuck himself. So what that means, there is an incredible, I really should have edited that slide a bit more. There is a trade-off between availability and reliability. This is some enormous contention here. In fact, this is actually at the heart of the CAP theorem. Do I pick availability or do I pick reliability? Because they are practically XOR. This, by the way, is fantastic because this is a tremendously exciting place to be as a computer scientist, being able to surf the wave between availability and reliability and get paid for it. Thanks, man. So the question is, should my system be reliable or available? The answer is it depends. There's no one size fits all, but we can have a look at when we might go one way or the other. So for example, in most databases, particularly those SQL databases, when we have aggregates, documents or keys and values or columns or whatever, what we tend to have in those systems is eventual consistency. And what that means is if I write a value into the database, at some point later in time, all of the replicas that hold that value will eventually agree. So you get consistency of a value across replicas. That's nice. And there's a window of opportunity where the replicas may be inconsistent, but on the whole, we iterate towards consistency. That's fine. It's a trade-off. The trade-off we're making there is that we can get potentially great write performance, but we don't get a reliable answer, classically in fault tolerance terms. Now, I think the distributed database community has done a lot of good stuff there. They've worked on things like clocks and timestamps. They start to reason about causality. They've worked on CRDTs or mergeable data types, and there's a lot of good stuff happening there. But ultimately, all we do is agree that one single value is replicated eventually to all of the replicas. In computer science terms, that's a relatively known problem. It's a relatively solved problem. In graph databases, though, the problem's a bit harder. So you guys have been exposed to Neo4j, you're Neo4j users, you've done some Neo4j stuff today or heard talks about it. In Neo4j, when we're traversing across relationships, we can do it in either direction and go from node A to node B, or we can go from node B to node A. And the point is that doing that in Neo4j is constant and cheap cost, whichever way we go. Now imagine if I represented those records thusly. So if I was in an aggregate store and I wanted to represent that relationship like I have here. So here we have a classic geopolitics problem. We have the United Kingdom loves the United States. And you can see here that the aggregate representing the UK has an outgoing loves relation. And you can see the reciprocal of it here. The node representing the UA has an incoming loves relationship from node ID 1. There you go. So whichever of these records you happen to read, you will get that there is a loves relationship between these two records, right? Awesome. USA, USA. Yeah, you can see why we're quite so friendly, right? Anyway, what happens if some enemy nation decides to start messing with our data? I don't know, man. I just Googled for people who don't like Brits, and that was the only flag that came up. We're otherwise such a welcoming and friendly nation. So anyway, let's say that the French, for example, decided to start messing with this data. Let's say that they were concurrently updating this record as we, the Brits, are updating this record. So you can see now that we've decided to qualify our love for the Americans to be full. Obviously, because we don't want to be drone attacked at any point. We're just gushing with our love and affection. But over here, you can see that the French have decided to remove that link. My French colleagues hate this bit. So what does this mean? I mean, if I end up reading the graph from this direction, if I'm America checking who loves me, if I read from this direction, hey, the Brits love me, it's all good. But if I'm American and I read from this direction, it's like, oh, well, the Brits don't love me, let's drone attack them quickly. This is a problem, right? So it turns out that, you know, if you've got two concurrent threads, both addressing semantically equivalent parts of the data, you need to get consistency of 2. And you need to be able to reason about ordering. You need to, in a distributed system, you have to be able to say A before B or B before A. And if all you have is eventual consistency to depend on, this is a problem, because you've now got a completely random behavior, right? It's completely unpredictable. Do we get drone attacked or not? These are things I need to know. I've got family. Leading to, yeah, the UK reads the loves relationship that exists, then feels safe and warm, or then it goes, does it exist, does it not? These changes across these disparate records may not even make sense from a domain perspective. They may violate some domain invariance. But because all we have is eventual consistency, these inconsistencies and this non-determinism embed themselves in the graph. And there's a worse thing once you embed like one inconsistency in a graph. Graphs are great at spreading pathogens, so that one inconsistency spreads through the graph and creates more and more inconsistencies as you compound that problem. It is effectively, let's nuke Britain, which will be fine if UKIP win. So we have to start resetting some of our expectations about what we want from a database. We can't simply piggyback the beautiful cipher on some blah, blah, blah distributed key value store. So whereas it was obvious that obviously we wanted eventually consistent over right consistent, no, we need right consistency of 2, and we need to do that fast. Do we want base over acid? No, but fortunately the transactions community has done a lot of work in the last few years to make sure that you can have highly concurrent, high performance acid transactions without sacrificing base. And we want perhaps partition data over single image, perhaps. Single image does provide the performance advantages of being able to do pointer chasing. This is a surprise. But you want to watch it again, right? That's the horrible thing. It's not my kid, fine, kid can cry. Okay, I can't watch it anymore. So for graphs, actually reliability is the more important aspect than availability. But you might say, but I've heard about this other thing that just does, no. But no, right? Read FLP, read the Leon Anderson work, no. What does that mean? It means we can't naively just try and impose a graph model on a non-native database because it doesn't have the mechanical affordances to keep our data reliable. Boo. See, this is the sad bit. That's why it's Empire Strikes Back. It's like, oh, wow, way to end the section, Jim. Still, Return of the Jedi. Bit more upbeat. Got a bathrobe. It's all good. Did everyone have a bathrobe when they were kids? And they're like, Jedi, awesome. So, Return of the Jedi. Of course, the most important thing that we know from Return of the Jedi is it was the genesis of Jar Jar Binks, which we could have stopped. We could have done that. We should have done that. Actually, I've got no more Star Wars things. I just hate Ewoks. I just needed to get that off my chest. So, we've been doing a bunch of engineering work at Neo. Hey, Brits. Actually, top-notch Ian Robinson knows this guy for real, so awesome. So the Neo engineering team has been doing a bunch of really interesting stuff. So we are working on larger databases. So you guys say, my ambition today is billions, I want trillions. We're going to do that. We're going to work on even faster Cypher. The Cypher team has done some amazing things in terms of query planning and optimization. They're now building a high-performance runtime for Cypher. We've got better internals. You've seen if you've gone into production with Neo4j that you get a high-performance lock manager. You also see that our new cache that our kernel team built has provided a storming increase in performance. And in the near future, our engineers working on the binary and remoting protocols are going to give you some absolutely sweet kick-ass drivers in your language. You're going to see bigger data, faster queries, more queries, better predictability, and native, high-throughput, low-latency drivers. That's just from the engineering side. How? Because it's graph native all the way down. We can optimize for graph workloads because we are not depending on some other database to do the heavy lifting. This is all about going from the socket down to the disks and back in a way that is sympathetic to graphs. That's what gives Neo its performance and reliability edge. And we like it that way. But then we've got the sciencey bit. Right, so in the future, we're going to be doing, because your ambition is not going to stay static, we're going to give you the remoting stuff, and you're going to suck up that capacity because you're going to get more ambitious. So we need to be one step ahead of you so that your ambition can continue to grow and we can continue to serve you. So next, we're going to go with peer-to-peer clusters. We're going to go for massively concurrent ACID transactions across those machines. We are not going to sacrifice the reliability of your database just because some people thought two-phase commit was slow in the fast. We're going to have caches that are graph-affine, that understand locality. We're going to have domain-specific partitioning. We're going to have all of that, and we're going to do it reliably. Because in sacrificing reliability, all we get is corruption. What we're not going to do is this. We might do. He'll have forgotten this slide by the time we tell him anyway. Let's tell him we beat cap theorem. You can't beat cap theorem. It's a theorem. It's not a conjecture anymore. I like this. It's good I can do this talk here in London. I show this slide in the United States. They're like, I don't know, what is it? Baltimore, I don't know. So actually, we think it's better to design for reliability and accept that availability may be a casualty, because availability doesn't have to be a binary function. Even when an escalator has no power, it still functions as steps. So you can get graceful degradation of service. Occasionally, you do get pathological failures. That looks super painful, right? Occasionally, you get pathological failures, and we will perhaps become, bits of your graph will become unavailable. But at least it will just be transiently unavailable and not permanently corrupted. And oh boy, do we like that. Yeah, we like that. I wonder who she's going to ordain tomorrow. So this stuff is not easy. This stuff is not at all easy. In fact, it's splitting graphs, transaction protocols, all that kind of stuff. It's super hard. In fact, the partitioning stuff is NP complete. It's a tough problem. But we're not doing it because it's easy. And we're not going to do this in an afternoon of hacking. This is a kind of long-term trajectory. This is a roadmap that you guys can trust, that as your levels of ambition rise, our level of technology rises to support you, ahead of you, but always giving you guys the headroom that you need to build your ambitious systems, because we build Neo4j as an ambitious system ourselves. In fact, we don't think this stuff is impossible, because in the graph space today, you guys are already building systems that would have been thought impossible or impractical just a few years ago, and now you've plugged in this kind of stupidly badly named database, and suddenly things become, it's a great name, great name. So, this extremely Googleable database. See? From adversity to triumph. You guys are already building quite ambitious things today that would have been impossible or impractical just a few years ago. And we want you to continue to raise your level of ambition so that you can build things that you think are impossible or impractical today. You'll be able to build those things tomorrow. Because we think that impossible is not a fact. We like Muhammad Ali. It's an opinion. Impossible is not a declaration, it's a dare. Impossible is potential. Impossible is temporary. Impossible is nothing, brackets, with graphs. Time for graph beers, people. Let's see you out there for a nice cool drink of beer. And thank you for coming.